Hi, everybody, and welcome to the screening of the first 24 minutes of A Sea Change, which is the first documentary to focus exclusively on ocean acidification. My name is Maria Jose Viñas, and I have nothing to do with the production of this film. I am a press officer for the American Geophysical Union, and my relationship with this film is that the filmmakers asked me to screen it at the fall meeting in December 2008. So we organized a similar event. It was, we also showed like 25 minutes, and after that there was a panel discussion with 4 scientists who were featured in the film. And the event went very well. We got a lot of questions from the audience, and the filmmakers got a lot of requests for more screenings and contacts. So they have asked me to introduce the panelists and moderate the discussion after the screening. So when the film was complete in March, it was also shown at the National Museum of Natural History in Washington, D.C. The room was 565 seats, and it was full. In the audience, there was NOAA's director, Jane Lovchenko, so it was a complete success. And right now, the filmmakers are showing the film at various festivals, together with NGOs, environmental and advocacy organizations, and they are trying to sell the film to PBS and some European public broadcast stations. So if anybody in the audience is interested in organizing a screening, they can talk to me afterwards and give me their contact information, and I will pass it along to the filmmakers. So first we will play the segment, and then I will introduce the panelists, and you can ask them questions. Hope this works. Okay.
I feel like I'm in the water. What are those bubbles for?
So they get oxygen. What is this creature down on the bottom?
A sunfish.
Is it?
Yeah.
That's right, you're right.
Oh. 10, 11, 12, 13, 14, 15, 16. There's some over here that are teeny.
That is so beautiful.
Look, one broke. What I feel? I wish I was a fish.
You wish you were a fish?
There are massive, unrecognized changes of geologic scale taking place in the ocean. Ocean chemistry is being altered on a scale not seen for millions of years, and we don't know what the consequences will be.
We are heading into some pretty dangerous territory here.
It's not just the magnitude of the change, it's the rate of change that species can't adapt to.
I think we've gone past the point now whereby we can avoid losing significant species. We're playing poker. If we lose at the poker, we could have a lot of problems for civilization.
We now know that the absorption of carbon dioxide actually changes the very chemistry of our oceans. We risk not just damaging the ocean's ecosystem, we are threatening its very foundation.
You're singing as well?
Look where you're going. Look where you're going. Keep your eyes. Stop.
I'm ready to stop on the bike.
I don't want to go on the bike. Could I help you do better? Okay.
This is my grandson, Elias.
I'm Elias.
Elias calls me Bestefar, which is grandfather in Norwegian. Elias is a mischievous rascal. He's smart, he's inventive, and he's the kind of grandson that anyone would want.
I'll help you.
You want to carry the front end?
I am now a retired educator who spends more time than I probably should thinking about my grandchildren and what their lives are going to be like. I continue to try to understand what's going on environmentally, and I worry a lot about the world that Elias is inheriting. One weekend, after Elias and his family had been visiting, I opened an issue of The New Yorker and read the article by Elizabeth Colbert called The Darkening Sea, about this phenomenon I'd never heard of, called ocean acidification. I knew that modern technology had made it easier for the oceans to be overfished. What I didn't know was that so much of the carbon dioxide was falling into the ocean and creating a horrible problem. I clearly need more answers, and I need to go to the source.
Elizabeth Van Husevik.
I have to tell you, I read this article last November that you had written for The New Yorker. I hope I'm not overstating it, but my life really hasn't been the same since. I have become somewhat obsessed with ocean acidification.
There was this huge untold story, that people really didn't know. They knew about global warming, vaguely, in sort of this mushy way, but they really just had no idea about what was happening to the oceans. People like me sort of try to translate it, and on some level, ocean acidification it's just the flip side of global warming. Whatever you put into the air ends up in the ocean. We're really talking about very radical changes. It's huge. I mean, the hugeness, it's everything. It really is everything about how we live.
I want to try to figure out how to talk to at least my oldest grandson, who's old enough to begin to understand this.
Yeah.
And I'm curious whether you ever have this discussion with your own children.
My kids are very aware of things. One of them said to me the other day, this is the problem with being born so late. That the world is really a, degraded place. And that was sad for a parent.
Mm-hmm.
If there's any issue that really demands that we acknowledge our interconnectedness, it's this one.
There are now 387 parts per million of CO2 in the air. The highest figure we've had in 650,000 years. I just can't believe that. Pteropods are tiny marine organisms at the bottom of the food chain. About the size of a child's fingernail. Wow. Oh boy. Known as sea butterflies, they swim by a pair of wing-like flaps and grow delicate shells for protection. Look at that. Look at that. I had store them. Their shells, however, are beginning to dissolve from the ocean's changing chemistry, and this is threatening the entire food chain. Dear Elias, today I'm starting a journey. And the purpose of this journey is to find out some things about the world's oceans that I don't really understand. I'm on my way to Seattle, where I spent a good deal of my own childhood. It is by the time when we would move back to Norway. But the way it turned out, that so-called right time never came. Hi, Elias. It's Bestified.
Hi, Bestified.
How are you?
Good.
Well, I'm out in Seattle. I'm going to send you a postcard every day while we're out here, okay?
Okay.
Are there any special kinds of postcards you want me to send you? Like fishes or boats?
I'd like a dinosaur postcard.
I see. Okay, well, I'll look for one of those. Tomorrow I'll be going to a conference, and there'll be lots of people there like your papa. Lots of professors. And they're going to talk about whether the oceans are healthy or whether they have problems.
This is a kind of a historic moment. For the first time, we're bringing together all the scientists that actually work on this problem for the Pacific Northwest. We're very fortunate to have many of the leading researchers in this field participating today.
From a fishing industry point of view, acidification is an unambiguous threat. This is a short look at what's at stake. 60 to 100 billion bucks in seafood trade worldwide. U.S. commercial fisheries are valued at about 28 plus billion. If you're a shellfish, you're in trouble. And most of the things that the fish we like to eat, they eat some kind of shellfish. When you show that pteropods start dissolving within 48 hours in the water we already have in the Gulf of Alaska, that's not slight. That's not some future prospect. That's now.
We, the scientific communities, were wrong. We had underestimated both the magnitude and the rate of global climate change. Are we involved in another mass extinction event for corals, for instance? When such events take place, it takes millions of years for the corals to come back.
Are we screwed? Is it already too late?
Are we screwed? Yeah, to a considerable extent. A world of 500 ppm is a world of enormous environmental destruction. We ought to recognize that and say it. And we cannot stop there. That is not an acceptable final threshold. But can we do any better than that now? I don't know. If there are ways of dealing with it, the knowledge will come from you.
I know you're only 5 years old, Elias, so I may not send this letter until you're much older. I'm writing to share with you my worries about what my generation is leaving to yours. I'm 65 now, and when you're ready to read this, you might well ask what I did to help solve this problem. I really believe, Elias, that the most important thing is to gather as much information as possible to pass on to you and others about what is happening in our oceans. My life has taught me that the power to affect change begins with knowledge.
What do we got here? I mean, it looks like we have Rube Goldberg working in the back room. What is this?
We have all the components to study ocean acidification for the very first time together on this morning.
We've moved well beyond just figuring out what's the temperature change. There are chemistry changes, there are ecosystem changes, there are biological changes. All of these things are happening all at once.
We always thought of CO2 as a waste product of all of the production of fossil fuels from coal and oil and automobiles. We just dumped it into the atmosphere and we said, no problem, the oceans will suck it up. And sure enough, the oceans do suck it up.
We first approached all this with the idea that, wow, the oceans are performing this tremendous service for humankind. It's absorbing 22 million pounds of CO2 a day. So we first approached this saying, great, let's go figure out how this is working. Maybe we can enhance it. It wasn't until we got out there and actually quantified that the oceans have absorbed 118 billion metric tons of carbon dioxide. A metric ton is about how much a small car weighs. That we've put the equivalent of 118 billion VW bugs worth of CO2 into the ocean over the last 200 years. And 43% of that has happened just in the last 20 years. And it's growing exponentially. As we start to project out into the future, it really gets scary. And people say, oh, well, the oceans are huge. We could never really affect the oceans. Well, we are.
They are changing.
They are changing, and we're measuring it. We're actually documenting that.
I'm on my way to Alaska now, where I haven't been in 55 years. I have mixed feelings about returning after so long. I remember our time there as one of hardship and one of yearning to get back to Norway. This time I'm meeting with Jeff Short, one of the scientists at the conference. He has a young son, and I'm hoping they can share with me something about how they talk together about these difficult issues.
In winter, sometimes it gets pretty nippy. In the city, it's all noisy. It's not as quiet. There's more pollution. Here, it's pretty fresh and clean. I like all the wildlife. You can see different species of fish out in the water. Sometimes you can see whales. And there's too many different species of bugs to even count. It's really neat. I like the glacier a lot. It's like this big lake at the bottom of it. And there's this huge waterfall pouring into the lake, and there's these oddly shaped icebergs. Some look like battleships. Then there's this big ice cliff with cracks in it, and there's just this huge ice field. It's not as big as it used to be, but...
We have tried to not hide from him the fact that the planet is going to undergo unprecedented change over the course of his lifetime. It's a tremendously high-stakes crapshoot, and the more acid we put in the ocean, the more likely it is that fundamentally bad things will happen. Like, for example, no more shellfish or no more coral reefs. And this is, for as far as humans are concerned, no more of those things ever. We've always had crises to face. Every generation has had terrible crises to face. When I grew up, it was nuclear war. We were worried about, we had these drills in school. There were going to be atomic bombs. People had shelters, and it was a real fear. This is, I think, a worse fear, because that's a political problem that you can solve by talking amongst people, and that largely has occurred so far. This isn't something that you can't talk nature out of this. We've been in this very stable environment climatologically for the last 20,000 years, and now we're committed to leaving that stable environment, and we don't really know where we're going to go, but we do know it's going to get a lot more variable, and a lot of things are going to die. There's going to be a lot of extinctions.
I wanted to go someplace where I could see what the effects of ocean acidification might feel like to people. So I visited Cordova, Alaska, where they had an environmental disaster nearly 20 years ago. As it happened, I arrived at a time when the salmon were coming home to spawn.
going on out here? I mean, I've never seen this before. What is this?
The pink salmon have returned, and that's
what we see jumping out here.
That's what's jumping like popcorn right now. And the scientists don't know why they jump. One of the theories is they're trying to loosen the egg sacs before they spawn. Maybe they're just happy. I mean, they survived 2 years in the ocean. They're the few, the small percentage that made it all the way back.
What do we have up here behind us?
Well, this actually was one of the largest salmon canneries. It went bankrupt after the oil spill. It was a tremendous loss for this area. The year the Exxon Valdez hit was such an emotionally devastating time for this community.
Valdez traffic. Yeah, we've fetched up on the ground. And evidently, we get some oil. And we're going to be here for a while.
The whole ocean is so sensitive that makes a huge difference, all the way from the bottom of the ecosystem to the very top predators. I watched this community just unraveling. Everything that we knew as normal just suddenly wasn't. Our whole world had turned upside down. I think the way that ocean acidification will hit these rural communities will be very similar to what happened with the oil spill. I worry that it will tear these communities apart with the same types of destructive behaviors, abuse, self-abuse, abuse to the families, abuse, polarization, fighting that we saw after the oil spill. And because this problem is actually so much bigger. In terms of like ocean acidification, I mean, first there has to be the recognition that this is a crisis. And I'm afraid the call for alarm might come too close to the end where we can't change it.
I get it. I get it.
How do you think we should talk to our children and grandchildren about this?
I think of what Einstein said. No problem can be solved from the same consciousness that created it. And on one hand, I look at what's going on in Washington, D.C. Stay the course, drill the planet, oil shales, no regard for the consequences of water, people's lives.
It is one species. It is a chain reaction here, everything relies on something else, so.
What do you think we need to do?
You just have to cut CO2 emissions. That's, I think, probably the only way.
It's the cause of all our problems.
Okay, so I believe that the feature film is 90 minutes long, and if you would be interested in screening it at your institution, please get in touch with the filmmakers in www.acidification.net. So now I'm going to introduce the panelists, and there will be a discussion on ocean acidification. Jelle Bijma has a background in marine biology, and he is the editor of the EGU journal Geosciences. He's also responsible for writing the EGU position statement on ocean acidification and the European Science Foundation Science Policy Briefing on ocean acidification too. And next to him, there is Gert-Jan Reichart, who does research in organic geochemistry at Utrecht University in the Netherlands. And he has studied past ocean acidifications. And finally, there is Michiko Hama, who is the communications coordinator for the European Collaborative Research Scheme at the European Science Foundation. So if you have questions, there is a microphone. Yeah. Micro?
Hi there. Jonathan Leake from the Sunday Times of London. What kind of modelling work has been done on acidification, and how much modelling work is needed to know how fast it'll progress and where it'll hit hardest?
Say the only good thing about ocean acidification is that we can predict the change in the chemistry of the ocean very precisely based on given CO2 emission scenarios. And it has been modeled with great accuracy. Basically, you could use the business as usual scenario and then see what's going to happen in the world ocean. Well, you probably know that CO2 dissolves better in cold water than in warm water. So the high latitudes will be affected first, and that's within the next 20 to 30 years. It's projected that the Arctic and Antarctic regions will be undersaturated with respect to calcium carbonate, which is a mineral that is secreted by many organisms like the pteropods that were shown, but also ostracods, foraminifera, many plankton species that are at the base of the food web.
I get the point. I know, I get the chemistry. I was just curious. I mean, the reason I asked the question is I went to the Copenhagen Climate Conference recently, and there were a lot of assertions made by scientists there about ice dynamics. And it turned out that although what they were putting forward was very reasonable, the underlying modelling hadn't been done, and they were kind of hypothesizing more than making firm predictions. And I was just curious to know whether, in the case of acidification, you actually feel there's a need for more modelling, or if you've got a very good idea of what's happening, or if you're working from a kind of first principles basis rather than actually having done a lot of work on what will happen and where. I mean, what can we say about the Antarctic or the Arctic, or you know, can we be more specific and are there any specific predictions based on computer modelling or other information?
Yes, there are papers by Dick Feely, you know, one of the people that was shown here, Jim Orr. They've been published in Science, in Nature, and they demonstrate that the ocean is going to acidify more and more. And you have to see that acidification sounds as if the ocean becomes acid, but it's not. It's still alkaline, but it's acidifying, and the reactions in the ocean, the chemistry behind it, is really straightforward. So there is no question whatsoever that these models give you the right prediction. This is not a highly non-linear process. It's very straightforward.
Could you comment on the significance of geological records that might provide analogues for a future with higher atmospheric CO2 and an impact on ocean chemistry?
Yeah, I think one of the best known examples of a geological analog is the PETM, where you see this massive dissolution of carbonates on the seafloor. Of course, PETM is probably triggered initially by the massive release of methane, but after that it had been oxidized to CO2. At the same time, you see that the CO2 is resorbed by the oceans, and then you see that basically the whole level at which calcium carbonate dissolves shallows like a couple of kilometers. So basically you see that almost the whole ocean becomes undersaturated with respect to calcium carbonate. And that's also the time that you have the largest benthic extinction of the last, well, 70 million years or so.
Maybe we should add that PETM stands for Paleocene-Eocene Thermal Maximum, which is a time period 55 million years ago, right? Yeah.
Hi, Sam Illingworth, University of Leicester. Just wondering if it really is as simple as cut the CO2 emissions, or if there's anything else that's being done or that we're doing now to try and address this rather horrific problem?
Could you repeat that question, please? I didn't.
Yeah, sorry. Is there anything else that's being done or needs to be done apart from reducing the CO2 emissions?
The only reason for, well, let's put it this way. The ocean acidification is something that comes on top of all the other problems we already have. It has been argued for a long time that climate change or global warming was maybe not due to CO2 alone, and maybe not due to CO2 anyways. You remember that in the States under the Bush government, people refused to accept the idea that CO2 is behind this. In the case of ocean acidification, we know, like I just said before, it's a very simple reaction. CO2 is absorbed, and the thing is, it's not, CO2 does not react as another gas, such as oxygen or nitrogen, but it and simply dissolves in the water, but it reacts with water, and in fact, the dissolved part of the CO2 is less than 1%. All the rest is in the form of bicarbonate or carbonate, which is a consequence of deprotonation of carbonic acid that forms when CO2 dissolves. So the only reason for ocean acidification is the absorption of CO2 by the ocean. So if we keep on producing CO2, it will get more and more acid. There's nothing else that you could do than stop the production or the emission of CO2 to the atmosphere.
Is there nothing else we can do as well as that, though, to try and reverse the process?
Well, she just gave me a note going to geoengineering. There are a lot of solutions proposed by scientists for mitigating global warming. Things like producing CO2 aerosols in the atmosphere, producing big umbrellas in space, reflecting the sunlight, the incoming radiation. But for ocean acidification, there is not a geoengineering solution.
Thank you. Jean de Pomeroy, International Polar Foundation. There have been some papers, I forget by who exactly, about the fact that the oceans, in particular the Southern Ocean, may become saturated with CO2, and that the process may, in fact, at that point reverse, and that the ocean might start to release CO2, aggravating the problem even more. Can you comment on that?
Yes, there are two aspects. One is that and this is sort of counterintuitive, because the carbon chemistry is very difficult to understand intuitively. When organisms secrete calcium carbonate, at first glance you would think they take up CO2, but in fact the carbonate is such that by secreting a calcium carbonate shell, you are producing CO2, because you take out alkalinity. It's difficult to go into that. You just have to believe me that that's the case. So what happens is that if these calcifying organisms, which are the first ones to go, if they don't secrete their shells, they produce less CO2 to the atmosphere. So it would be more of a sink. On the other hand, these calcifying organisms, they work as a ballast for the organic matter that's being produced by photosynthesis. This is what we call the biological pump. And they ballast this material and transport it effectively to the ocean interior, thereby taking CO2 from the surface ocean to the deep ocean. That's why it's called the pump, because it's pumping against the gradient. So if all biology would stop, which has been called the Swertlov Ocean? Strangelove Ocean. Then within 200 years, the PCO2 would increase by a factor of 2.5. So this pump is very important, and if these calcifying organisms are not there anymore, then it's difficult to predict how the change of the pump would be. So what may happen is that more CO2 will remain in the atmosphere and not be transported to the ocean interior. Okay? So that would increase the impact of global warming.
Hi, my name is Horst Panzman from the Australian National University in Canberra, in Australia. My question would be, as far as I understand, the change in ocean temperatures also changes the global circulation of the ocean currents quite substantially in the long run. If this happens, the transport of CO2 in the upper layer of the ocean to the lower layers will also be affected quite dramatically. How much of an uncertainty is this in the modeling of the long-term acidification? Do you have an idea about that? Could you comment on that?
Yeah, I think this definitely will have an effect on the uptake of CO2. But I think this is all the kind of things that have to be addressed. This has not been modeled yet. This is all the kind of, just as Jelle explained, the overall picture of what's going to happen is quite clear. But if you on top of that add things like which are induced by climate change, then the whole circumstances become much more difficult and more complicated to understand.
It's been suggested that there will be a transition in the Arctic to continually seasonally sea ice-free conditions, perhaps within the next 20 to 30 years. Could you comment on the significance of this for gas exchange and perhaps acidification in the Arctic?
That's a very good point, and that's also something which desperately needs to be addressed in studies, because this is the extent of sea ice, of course, and not only in the Arctic, but especially also around the Antarctic, has a major impact on the exchange of CO2 between the oceans and the atmosphere.
So I asked Jelle to comment on EGU's position statement on ocean acidification.
Well, basically, I think the movie that we just saw is mostly about communication, in fact. How do I communicate the problems that we face to the younger generation? Statement. This position statement was one of the results from a workshop that we had organized in January 2008, which was an ESF exploratory workshop. And we had set out two goals. One was to come up with a science policy briefing for the European Science Foundation. And the other was to start up a program that would be run by the European Science Foundation on ocean acidification. Now, you may realize that the whole complex of global change has started decades ago. And in fact, I should mention that in the 1960s, already Wally Broker said that, this CO2 that we are producing might, at some point, turn the ocean more acid. And that was already 50 years ago. But the research on ocean acidification started maybe 10 years ago. And as we saw in the case of global change, global warming, only after the Stern report, all of a sudden politicians started to listen, because it could have an impact on economy. And the impact on economy was bigger than people had thought. So we started off and said we need to have economists and social scientists in the working group and come up with something that also addresses the economic and social sides of this. Now it turns out that there's only a few economists, I counted 3, working on the issue of ocean acidification. And we couldn't get them at that point in time. So it has taken a long time now to, from this initial meeting, through multiple stages of reviewing and asking economists to add their things. Turns out that based on the impact of ocean acidification on coral reefs alone, the economic impact is about an order of magnitude smaller than the impact of the economic impact of global warming, global change. But that's only on coral reefs, and coral reefs are a small part of the whole marine ecosystem, which may be much more dangerous is the impact of ocean acidification on the basis of the food chain or the ecosystem and all the impacts that it will have. So the ESF science policy briefing we delivered, in fact, 2 weeks ago, and now we're waiting for the last standing committee to respond to that. We hope that this will be ready by the time or before the start of the negotiations in Copenhagen this fall. But we had enough information to come up with a policy statement on ocean acidification from the side of the EGU. So that's what we did, I guess, a couple of months ago. That can be read on the webpage.
Mark Lawrence from the Max Planck Institute for Chemistry in Mines. I've been working for about the last decade at providing information to policymakers on the side effects of ocean fertilization, ocean iron fertilization, and especially the side effects on the atmosphere. Plankton not only are involved in the carbon cycle, but they produce all sorts of other gases like dimethyl sulfide, isoprene, organohalogens, and when they decay the bacteria produce nitrous oxide, which is a very potent greenhouse gas. It didn't occur to me until after this presentation that the ocean acidification, because of the changes that it makes in plankton speciation, might have a very strong influence on these other gases. Do you know if anybody has looked at that yet, or has that come into the mainstream? For instance, could there be a substantial pulse in nitrous oxide through ocean acidification?
Well, what has been observed is that there are large changes in the microbial communities due to changes in ocean acidification. And especially nitrogen-fixing bacteria seem to profit from ocean acidification. So I think it will have a large effect, although this is only a very few, the data on this is very limited. So this is only just beginning.
Hi there, yeah, Jonathan Leake, Science Editor of Sunday Times again. I wonder if you feel able to sort of paint a picture, as it were, of what the oceans might be like in 100 years' time, say, if we carry on a business as usual scenario. It's quite, although people in this room might listen to what you're saying about the ocean chemistry and the changes in plankton, it's not very evocative. It doesn't tell people who are non-scientists what really that's going to mean. So, say in 50 or 100 years' time, let's assume we have a business as usual scenario and we carry on doing what we're doing. What kind of oceans will we have then? And just as a corollary to that, ocean acidification didn't play much part in the last IPCC report. It got a couple of mentions, but wasn't very big. What do you think's needed in the next IPCC report? And above all, what do you think's needed at Copenhagen?
Say that the last one.
In Copenhagen at the climate talks this December.
Well, first to your question, what does the ocean look like in 100 years from now? The simple answer is we don't know. Like I said, the chemistry can be well predicted, but the response of the organisms is very, very difficult to predict at this point of time. In fact, just about a year ago, a European project called EPOCA started, and this is the first project that looks into the impact of ocean acidification on biology. We have, like Gert-Jan was saying, we have analogs in the past, but the thing is that the rate of change during the PTM, during the Paleocene-Eocene thermal maximum, was probably 100 times slower than we do it today. We are really good in changing things very, very fast. And we don't know if biology is going to adapt. And we don't know how the impact of both changes in the, it's not only the temperature of the ocean, it's also the mixed layer depth, it's the acidification. We are just at the basis of learning how some species might react. So it's very difficult to say. And then regarding your question, what needs to be done, what do we need in the Copenhagen meeting? I hope that we get very strict ideas or strict policies about CO2 mitigation and things like that, because now we have, in addition to global warming, we have something that is directly related to CO2, and it is something where we don't know what the outcome is going to be, but we don't know for sure, but we have an idea about what could happen.
Oscar Romero, University of Granada, Spain. I'm missing in this debate and in the movie a very important point, which is the role and the effect of acidification on siliceous organisms. You know, in the ocean you have not only calcareous organisms, but we also have diatoms, silicoflagellates, and radiolarian, which played a very important role in primary productivity and also in the CO2 exchange. So could you please comment on this?
There's two things with siliceous organisms, and one group of organisms that is very important for the marine food chain are the diatoms, and I know you know the diatoms very well. They're siliceous, and in general, opal has a better preservation as the water gets more acid, and opal dissolves more when it's more alkaline. So the preservation as such would be better, but we don't know how the physiology of the diatoms respond to ocean acidification. The thing is that for fish, that was shown here a lot, it may be that, for instance, yearling salmon, they have a menu of about 80% pteropods. If the pteropods are not there anymore, you know, my guess is that they will find something else to feed on, right? And in fact, for fish, the largest problem is probably overfishing and not so much ocean acidification as such. But for these unicellular organisms that are at the base of the food chains, like the diatoms and silicoflagellates or radiolarians, we don't know how their physiology is responding. And the pH, the global pH, pre-industrial was 8.2. At the moment we have a global pH of 8.1. And you would say, well, that's a tenth of a pH unit. But remember, it's a log scale. So that means that going from pH 8.2 to 8.1 is a change in acidity of 30%. Now, if we predict the change in PCO2 by the end of this century, which is somewhere between 800 to 1,000 ppm, and I'm sure that we will manage to get it higher even, that would indicate that the pH is going to change by another 0.2 units. And then we have changed the acidity of the ocean by 150% in a time frame that is 100 times faster than these organisms have seen since their evolution, since the beginning of their existence. And we don't know how the physiology of these organisms will be able to adapt or not. So it's not just a matter of preservation, better preservation of opal versus more dissolution of carbonates.
This will be the last question.
Well, what mostly is used is looking at the different preservation of calcium carbonate along a depth transect in the ocean, and then back calculating ocean chemistry, and using that then to calculate changes in the ocean chemistry. And if you look at atmospheric PCO2, people have been using tools like, for instance, boron isotopes and also carbon isotopes in alkanones. But of course, it's never of the same order of precision as you can do with ice cores if you go further back in time. But on the other hand, of course, the changes, if you look, for instance, at changes such as happened during the PTM, they are an order of magnitude larger than has ever been seen in the last million years or so.
Okay, we don't have more time. Thank you all for coming, and if you want me to pass along some message to the filmmakers, please come by and give me your contact information. And thanks to the panelists for attending.